Hello, welcome. In this video I'm going to tell you about a new technique for solving differential equations. It's going to be the integrating factor technique. And the class of differential equations that we're going to be able to actually apply this to is somewhat narrow, but it is, these are differential equations that are not separable that we will be able to solve using this technique. Okay, so I think first I need to kind of point out for you what was the hallmark of being a separable differential equation, because that's, at this point, this is pretty much all we have. Aside from just like anti-differentiation with respect to the independent variable. So a separable differential equation is one where we can get rid of all of the y's and then hold all of the t's on one side and move the dt over. And so what it's going to need to be is that all of the t's and y's are going to need to be connected with multiplication. So we're going to need to be able to write y prime equal to some function of y times some function of g, so that we could get rid of the y's, hold the t's over here, get the dt over here, do our separation of variables thing that we're very familiar with from AP Calculus. So I would say that would be like f of y times g of t. Or at least could be written like that after, some factoring. Okay. Now, the integrating factor form this is going to be where we have y prime plus p of ty equals q of t. Okay. So, I could have said, f of t and g of t, but I've got two different functions of t. One of them is multiplied by y, one of them is not, and then I've got y prime by itself. Okay, this is something that we're going to be able to deal with. And so I think I'm going to solve it in general here, and then I'm going to do a couple of examples for you. All right, so if I want to start off, where's my notes? I want to start off with y prime plus p of ty equals q of t. What I'm going to need to do, and I've read about this before, I've taught this class a few times, and I've never seen who this technique is really attributed to, but every year I find myself, pretty impressed that, someone would just think to do this. It's really what we're looking at is we see a derivative of y here and a regular y there. And I don't know, I don't know that I would think of this, but there's another place where we'll see a derivative plus the original. And that's when we take the derivative of something using the product rule. But this is just like, this does not look like the derivative of anything after product rule. So what we're going to do is we're going to multiply both sides of this equation by some new function mu of t. Okay, just here's where the trust is going to come in. So you're going to say y prime, which is also a function of t, but I'm going to just leave y prime there, times mu of t plus p of t mu of t y equals q of t mu of t. All right, just multiply both sides of this equation by some mu of t, which is going to be the integrating factor. Okay, but you don't really know what that means yet. All right, now let's see. Okay, so I think off to the side, I want to point out that if we can figure out a situation where mu prime is equal to p of t mu of t, then we've got a product situation, a product rule situation. So if mu prime is equal to p of t mu of t, then this thing here, that I will underline in yellow, then maybe I'll write it like this: y prime mu plus p mu regular y. Well, that's going to be just the derivative of y times mu. If we can write mu prime equals p of t times mu. Now, if you think about it, we have seen a situation where the derivative is really close to the original, just multiplied maybe by some other function of t, and that would be when mu is an exponential function. So like e to the sum f of t. Because if we take the derivative of that, we're going to have e to the f of t multiplied by f prime of t. So somehow, if this p of t is anti-differentiable, we're going to be able to deal with this, okay? So at that point, I'm going to say, well, I'm going to use this equality, really just hoping that p of t is anti-differentiable. And so I'll say that this is the derivative with respect to t of y of t mu of t, where y of t is the solution I'm hoping to find in the first place, right? And this is equal to q of t times mu of t. Now, we're going to take the antiderivative of both sides with respect to t. So this will just be y of t mu of t. And then I'm going to anti-differentiate the right side. Now, hopefully q of t times mu of t is something I can anti-differentiate, but the odds are pretty good because we have a product rule for anti-differentiation. We can always do integration by parts. Oftentimes, this will be something that we can work with, especially since mu of t is going to be an exponential function, right? So this is going to be the antiderivative of q of t mu of t dt. And now, pretty much, I mean, all I'm going to need to do is divide both sides by this mu of t. Now, we are not going to be able to just like divide in the integrand. That's not going to be, that's not going to work. If you work through one of these, you'll see that just dividing in the integrand, it won't leave you with the same thing. That's what I'm going to say. I'm going to leave it at that. It will not leave you with this with the same solution. And then you could go and check the solution and make sure that we're right the way that we're doing it. Okay, but so the solution is going to be that y of t equals 1 over mu of t times the antiderivative of q of t mu of t dt. This is kind of like the steps that we're going to take to solve this differential equation. One of the big things that's going to happen here is that this antiderivative, we're going to, it's entirely in terms of t, so it's going to give us a new function of t, and then there's going to be a plus c. And then when we go to divide both sides by this mu of t, we're going to have to take that c and also divide that by the mu of t function, the integrating factor. So I think at this point, I need to give you an example and show you how this really works. So I'm going to actually slide over to the next one and set up for an example. All right, so for this one, we've got y prime plus half of y is half of e to the t over 3. So I'm going to pretty much like kind of respect the same steps that I took over there. And then I'm going to, and then we'll probably be able to see what the integrating factor is going to be in general, and then maybe you can use that when you go and solve these problems. So first thing I need to do is multiply both sides by mu of t, right? I'm probably just going to call this mu. So y prime mu plus 1/2 mu y equals 1/2 e to the t over 3 multiplied by mu. Okay? Now I'm going to look at this left side, and I'm going to say, look at this. This really feels like the derivative of something after the product rule, right? I'm going to say that, oh man, that just exploded. That's tough. I'm going to have to throw that away. Students slipping and falling later today. Okay, I need a new piece of yellow chalk. Hold on. All right, found a nub. This is going to look like the derivative with respect to t of y times mu if the derivative of mu is half of mu. Now, I think in the first video in this series, I told you that if we see a situation like this, it's like y prime is half of y, or f prime is half of f. That's going to be where mu of t is equal to e to the 1/2 t, right? dy dx equals k times y, that's exponential growth. Okay. So this is to say mu of t equals e to the t over 2. Okay. So this could be good, right? Maybe I will, just to be really explicit in this example, I'll go in and rewrite mu of t as e to the t over 2. I think that would be good. All right, so y prime e to the t over 2 plus 1/2 e to the t over 2y equals 1/2 e to the t over 3 e to the t over 2. A third plus a half, that's 5/6. So that's e to the 5t over 6. Okay. This is the derivative with respect to t of y times e to the t over 2, right? Because we can take the derivative of y, leave e to the t over 2 the same, and then add in, leaving y the same, the derivative of e to the t over 2 is e to the t over 2 divided by 2 for the chain rule. So I'm going to say that this is the derivative with respect to t of y times e to the t over 2, and that's equal to 1/2 e to the 5t over 6. Okay. I'm going to anti-differentiate both sides with respect to t, and I'm going to get y times e to the t over 2 equals, and I can take the antiderivative of this, it's going to be 1/2 e to the 5t over 6 times 6 over 5. So I've got 6/10 of e to the 5t over 6 plus some real number. Okay? And now to get at y, I'm going to have to divide both sides by this e to the t over 2, which, shouldn't be too bad. I can just say c e to the negative t over 2, and then I can just I'm going to subtract away those powers of e that I'd added in. So I'm going to have y of t equaling 6/10 is 3/5 e to the, well, okay, if I took 5t over 6 and I subtracted t over 2, I'm going to have t over 3 left, plus c e to the negative t over 2. Okay. Trying to remember, I think if we said, here, let me give you an initial condition. Y of 0 equals 1. And so I'll plug in 0 for t, 1 for y. 1 is equal to 3/5 times e to the 0 plus c times e to the 0. So c is going to need to be the 2/5 that's left over here. And I've got a particular solution, y of t equals 3/5 e to the t over 3 plus 2/5 e to the negative t over 2. And I'm happy. All right. I think before I move on and do another example, I want to just point out how this integrating factor technique went. Over here, my integrating factor mu of t ended up being e to the t over 2. What did t over 2 have to do with this up here, this p of t? Okay, t over 2 is the antiderivative of 1/2 with respect to t. And in general, we're going to see that happen on each of these integrating factor problems. That in general, we can say, let's get a different color of chalk, that mu of t is going to be e to the antiderivative of p of t with respect to t. Okay, that's how this is going to go. All right, so, I've got another example that I'm going to give you that has kind of an extra step, But one that I've just thought of that would definitely fit in with this, that we see somewhat regularly in AP Calculus, but is not separable, is the old-fashioned dy dx equals x plus y. So what I'm going to do is I'm going to say y prime equals y plus t. Okay, this could fit our mold here, right? We could use an integrating factor on this. Okay, I'm not going to give this an initial condition. Maybe I'll just look for a general solution to this thing. So I've got y prime minus y equals t. Okay, well, I know my integrating factor is mu equals e to the antiderivative of -1, I guess, dt, because my p of t, the function that's multiplied by y, looks like -1. And, okay, I can do this. That's e to the negative t. So, now, hold on. You might be saying, wait a second, dude, what about the plus c in this antiderivative here? Or when I did this, why was it not c e to the 1/2 t? That's a valid question. That's a question I took yesterday when I was delivering the lesson to actual people in the crowd, and I forgot to address it here. I think what I want to do is I want to tell you that we're not going to have to worry about it, work through the rest of this one, and then come back with a different color and show you what would happen if I did, say, c e to the t over 2, right? Or some other constant, k e to the t over 2. Really what's going to happen is it's going to be everywhere, so we could divide through by it and it would be gone. But I'll actually show you that happening. So y prime times e to the negative t. And really that's going to be e to the negative t plus c, which could become c e to the negative t, but we'll talk about that in a second. Okay, so y prime times e to the negative t minus y times e to the negative t equals t e to the negative t. Okay. Well, this is the derivative of y times e to the t. And then over here, well, I'm going to eventually be dealing with this using integration by parts. Okay. Didn't really foresee that happening, but you know, this might be just the right time to remind you about udv. So let's see, looking for a different color. Here we go. So, and over here, when I'm computing the antiderivative of t e to the negative t with respect to t, I'm going to let u equal t and dv be e to the negative t dt. Is this visible? Is it still in the shot? Yes, barely. Let's rotate a little bit. All right, and we know that the integral of, wait a second. Hold on, it's going to be negative e to the negative t. And we know that the antiderivative of u dv is equal to u times v minus the antiderivative of v du. So that's plus the antiderivative of e to the negative t dt. Okay. And then that's going to be minus e to the negative t. So negative t e to the negative t minus e to the negative t, you know, plus c. But I'll write that in down here. Or maybe I'll just drop this down to this line, yeah. How about that? All right, so when I anti-differentiate this, I'm going to get this antiderivative here. I anti-differentiate this side, I'm going to get y e to the t. And so I'm going to be able to get rid of the e to the t and just solve for my general solution. Y is going to be, when I divide by e to the t, I'm multiplying by e to the negative t. So I'll have negative t e to the negative 2t minus e to the negative 2t Hold on. This was supposed to be a negative t, so it needs to be here. And I'm going to be adding a power of e to the t. Yeah, this didn't feel right. So that's going to be e to the 0t, which is just going to be 1. Negative t minus e to the negative t times e to the positive t is going to be minus 1 plus c e to the negative, wait, no, positive t because I'm multiplying both sides by e to the t. Okay, sure I was having trouble with that. And this is the type of thing that if we took the derivative of it, we'd have y equals -1 plus c e to the t, which is that y plus t? Yes, it is. I've added that t and it goes, yeah, okay, I see it. It fits. You can check that on your own. Okay, back to the earlier point I was making about, wait a second, why is there not a plus c that comes with this anti-differentiation that's kind of implicit here? Okay. Well, suppose there was. Suppose I took this, and this was mu of t is equal to c e to the t over 2. Okay. Then, over here, everywhere where I have this e to the t over 2, I'd have c e to the t over 2. That 1/2 was still supposed to be there. Pardon me. So 1/2 mu y is 1/2 c e to the t over 2 y plus 1/2. Okay, what this was this was e to the t over 3 times c e to the t over 2. So this would have this would be 1/2 c. Still e to the 5t over 6. And then I could go through and divide this whole equation by that c, whatever it was, and it would just be gone, right? Okay, so that's why I'm not worrying about it in that case. You would see the same thing over here where I'd multiplied each side by e to the negative t. Had this instead been a c, I'd have a c here, here, and there, and I could divide them all away. Okay, I feel like that's going to be enough. Now I've got one more example for you. Yeah, and so the last example I've got for you is one that doesn't exactly fit the mold of a integrating factor technique differential equation, right? It's close, but it's not quite it, right? We want y prime plus p of ty equals q of t. All right, so what I'm going to need to do right off the bat is I need to divide both sides of this equation by that t, so I can just have y prime plus something involving t and y, and then something on the other side of the equation just to do with t. So what I'm going to do, divide both sides by t, get it into, we want to see the form y prime plus p of ty equals q of t, right? So that we know that our integrating factor is e to the antiderivative of p of t, and then we can just kind of motor on through this. So I'm going to say that y prime plus, and then when I divide t plus 1 by t, that's going to be 1 plus 1 over t. And that's going to be equal to, when I divide this by t, I'm going to have 2e to the negative t. Okay. Now, I know that my integrating factor is going to be mu of t equals e to the antiderivative of 1 plus 1 over t dt, which is going to be, that's going to be t plus log t. Okay. I'll do the algebra for you, just to remind you how this goes. Remember, x to the a times x to the b is x to the a plus b. So I'm going to say that this is e to the t times e to the log t. We know what e to the log t is, that's just t. So this is t e to the t. Okay. So I think I'm going to just get rid of this, fit it all on one line, and proclaim that this is t e to the t. All right? And now I'm going to go and I'm going to multiply that through as my integrating factor. So y prime times t e to the t plus 1 plus 1 over t, t e to the t, this one I have to take on faith, t e to the t y equals 2t e to the t e to the negative t is just 1. Okay, so that's kind of what I've got here. Now, this one you might have to, you could maybe grind through this and convince yourself of it, or you could just say that this is the derivative with respect to t. So it always ends up the same. Y times mu of t. Well, oh, I can kind of see it. Where this is all gonna come in. Yeah, because really if I distribute this in, this will be a t plus 1. And then you'll get that from the product rule if you factor out the e to the t. If you don't believe me, just take the derivative of this using the product rule and convince yourself. Okay. And that's going to be equal to 2t, which is something we can very easily anti-differentiate, right? And so when I do that, I'm going to have y times t e to the t equals t squared plus c. Okay. And I forgot to give you an initial condition again, but I believe that this one did come with one. I'm going to have to go back and look in the textbook and see what it was. All right, so I'm going to say y equals, honestly, I'm just going to leave it as t squared plus c over t e to the t, right? I think that's going to be the safest way to go. What was the initial condition that they gave in the book? Oh yeah, they said y of 1 equals some number a, and they wanted you to do some analysis on a. I'm going to say that y of 1 is equal to, I think 1 over e is what I need. Yeah. So okay, y of 1 is equal to 1 over e. Well, so that means that 1 over e is equal to, when t is 1, that's 1 plus c over 1 e to the 1. Well, that means c needs to equal 0. Okay, so I think in this case, y of t is equal to, well, t squared plus 0 divided by t, well, that's just going to be t over e to the t, or t e to the negative t. Okay, and there we go. Yes, that is going to be a sufficient number of examples. This is the integrating factor technique. It's the type of thing where if you do it a few times, you'll see it's very procedural, and it's definitely something that we can do with a high degree of accuracy.